Now we come to the actual thing. What is a boundary layer and how does it develop? So actually it was in 1905, 1904 or 1905, in that era, when the well-known scientist Prandtl, by the name Prandtl, and his students Ekman and Blasius and so on, they came up with the idea of separating the whole fluid flow into two parts. And when in a case that a potential flow is flowing across a solid body or past a solid body, then Prandtl thought of presenting this theory, this thought, that the flow field can be separated into two parts. One where the fluid is flowing very close to the solid body, and the second part when it is away from the solid body. As you can see here in the flow field situation, whereby a fluid is flowing from left to right direction past a solid body, which is shown by this oval shaped area, and the streamlines are flowing from left to right, then as can be expected that if the fluid is viscous, then close to the solid body, the streamlines are moving away. They are deviating a bit, moving away from it, and then coming back again, and then flowing. But away from this, away from the solid body, for example, at this point, the streamline that is passing, you don't see any effect as if there was a solid body present here. This streamline is almost like a streamline, like a straight line, and as if it doesn't know, the stream here does not know that there is a solid body lying away from here. So what is this happening and why this can be done? This has to do, there are many things that come into picture here, and we have to consider all of them simultaneously. One is the speed with which the fluid is flowing. The other is the viscosity of the fluid, that is important. Which fluid is flowing? If it is water, then it has a different velocity. If there is a different fluid, it will have a different velocity. And therefore, due to that effect of the viscosity, the boundary condition, the no-slip condition on the boundary line, on the boundary of the solid, there will be a no-stick position, no-slip position, and the fluid velocities will be zero there. And that is why you see this effect of the streamline. So the important thing is that which is that area where the viscosity is showing its existence and playing its role. And as we move away from the solid body, the effects of viscosity are reduced. And if we consider this situation, you will see that these are the things that we have to consider. Then the speed of the fluid is important, because we have to consider in the end what we call as Reynolds number, which is U into rho over mu. Mu is the coefficient of viscosity, U is the density, and so in a way this is the ratio. Reynolds number is the ratio of momentum forces and viscous forces. We call it as it's a non-dimensional number. We call it as a Reynolds number, as we have discussed it earlier. If it is large enough, that means if the viscosity is small enough, then we find that the flow field can be separated into two parts. One is boundary layer, which is close to this body, in the close neighborhood of this solid body, and away from it, the fluid behaves as if there is no solid body present in the flow field, and the effects of viscosity are small because the Reynolds number is rather high. Then again there is a question, how high is the Reynolds number? The Reynolds number needs to be high, but not so high that the flow field becomes turbulent. it has to be laminar. And you will recall that the turbulent flow, some scientists, mathematicians or researchers, they consider flow to be turbulent if the value of Reynolds number exceeds about 2200 or 2300. Some even at times consider it as 2300. So greater than that, if the Reynolds number is greater than that, the flow we call as turbulent, and for the values of Reynolds number less than 2200 is called as laminar. And the effect of viscosity obviously is small within that range. If the viscosity is large enough, then as you can see, u is the velocity of the fluid that is flowing, rho its density, and mu coefficient of viscosity. You can see from this ratio that if nu is big and if this is less than 1, then it is understood that the viscosity is playing a major role, and then the fluid flow wouldn't have that separation of the two zones that we were mentioning. So that can be seen here in the picture also, that as the fluid flow is moving, then the boundary layer exists in this area, in this small area which is close to the solid body. Outside that, the effects of boundary layer reduces. So they are not felt too much. So in this boundary layer region, as you can see here, this is shown as a large picture, enlarged picture from A to A dash, and you can see how the velocity is moving. And on the solid boundary, the velocity drops to almost zero. But away from it, as we go away from it, the velocity moved as if there is no solid body present in the flow field. But as we reach here, then naturally the velocity becomes close to zero, but not zero. Then again, the thickness of the boundary layer that we may call as delta x, normally denoted as delta x, and here shown within the red line, and the thickness of delta x is shown to you. Y and x are coordinates that are normal on the surface. X is a coordinate in the x direction, and y is a coordinate that is normal to the surface of the boundary of the solid boundary, because it has a curvature. So they are not rectilinear, but y is in the normal, and correspondingly there are velocity components u and v, u in the x direction and v in the y direction. So this region delta x is a small region where the effects of viscosity are felt, and this reflects the thickness of the boundary layer, and away from it the viscous effects are rather less. And then from the two-dimensional Navier-Stokes equation, which are written here, we try to calculate and make an estimate of the thickness delta x of boundary layer by looking at the dimensions of the various variables, which we will consider them. We will scale these variables and we see what is the order of the thickness of boundary layer.